Welcome. This is a lecture on binomial coefficients for Math 475. So remember, the binomial coefficients are defined by this formula: n choose k, n factorial over k factorial, n minus k factorial. These are called the binomial coefficients, and we've already discussed these in connection with some combinatorial problems. That is, specifically, this is the number of k subsets of an n set. Okay. We're going to revisit these today in a little bit of a different context. In particular, why are they called binomial coefficients? I'm not sure we've talked about this much. Well, it's the binomial theorem, which I suspect that everybody here knows. Here's the statement. If you take the polynomial x plus y to the n and expand it, what you get is the summation as k runs from 0 to n, of a polynomial in various powers of x and y, and the coefficients in that polynomial are these binomial coefficients n choose k. That's the binomial theorem. And now notice that these powers of x and y are such that those two numbers, k plus n minus k, adds up to n. So, for example, everyone knows that x plus y squared is x squared plus 2xy plus y squared. And that's because 2 choose 0 and 2 choose 1, 2 choose 2 are both 1, and 2 choose 1 is equal to 2. Okay, well, let's prove this theorem. It's easy enough. So how do you figure out what x plus y to the n is? Well, you multiply x plus y times itself n times. And in order to expand this as a polynomial, you have to multiply this out and expand all of the terms. And when you do that, you're going to get various terms. For example, you're going to get a term x to the k and another term y to the n minus k. And as I mentioned, the point is that the sum of these two numbers is n. And how many times are you going to get the term x to the k, y to the n minus k? Well, when you expand this, in the first parentheses, you have to choose x or y, and sometimes you'll choose x and sometimes you'll choose y. And you'll get an x to the k if you choose x k times. And, well, then you'll naturally also be choosing y n minus k times. And so what's the number of ways of doing that? N choose k. That is to say, the number of k subsets of an n set is exactly n choose k, as we've seen. So the binomial theorem really is just an application of this combinatorial formula. Okay, well, here's another proof. I always like to give two proofs if I can. This is a more computational proof. I'm going to proceed by induction on n. Well, let's check the case of 1. X plus y to the 1 is x plus y, which is, let's see, that's x to the 1, y to the 0, plus x to the 0, y to the 1, which is 1 choose 0 times x plus 1 choose 0 times y. So that's the correct formula in the case when n is equal to 1. So for induction, let's assume we know it for x plus y to the n, and write x plus y to the n plus 1 as x plus y times x plus y to the n. And now it's sort of obvious what you have to do: expand out the second term and then start manipulating. So the second term is the summation of n choose k, x to the k, y to the n minus k. And let's see, how are we going to work this out? Well, when you multiply it out, there's going to be a term that comes from multiplying this x times the summand, and that's going to raise the power of x. So you're going to get summation n choose k, x to the k plus 1, and the y is going to stay the same power. And then when you do the same thing with the y term, you're going to get a similar sum, except now the power of y is increased by 1. Okay, well, let's see. When you see something like this, you want to combine the two terms, and what you do is you change variables. And so you call this thing k plus 1, you call that equal to L. So you set L is equal to k plus 1, which means that k is equal to L minus 1. And you change variables, and the first sum now is a sum over L. And let's see, L is running from 1 to n plus 1, because L is k plus 1, and you're getting n, choose L minus 1, x to the L, y to the, let's see, n minus k is n minus L plus 1, or n plus 1 minus L. Are you sure about that? Let's see, where did I get that? So I need to change this n minus k to something involving L. What did I do? I wrote n minus k is equal to, let's see, n minus L minus 1. And that's the same thing as n plus 1 minus L. That's where I got the coefficient of y, the exponent of y. Now the second term, I'm just going to rename k and call it L. That's so I'm not really doing anything to the second term, just changing the letter so it matches the first one. And the point is that now I can match the two terms up. Notice that they both feature x to the L, y to the n plus 1 minus L. Okay, well, so these two terms are exactly the same. So I can split them off. And let's see, I have the sum from 1 to n. I can't go all the way up to n plus 1 because the other term only goes up to n. So when I pull out the same terms, I get x to the L, y to the n plus 1 minus L, and I only run from 1 to n. So I've missed a couple of terms. Let's see, what have I missed? Well, here I should have gone all the way up to n plus 1, and I only went up to n. So in order to make this correct, I have to add back in the term that I left off, which is when L is equal to n plus 1, which means that L minus 1 is equal to n. And so what I'm getting is n choose n, x to the n plus 1, y to the 0. All right, now in the second term, I should have started at 0, but I started at 1. So comparing those two terms, I see that in order to make things right, I have to add back in the term L is equal to 0 here, which gives me a plus n choose 0, x to the 0, y to the n plus 1. Okay, so, and I've underlined the red and blue to indicate where they came from. So let's see, this first term is, I'll write the n choose 0 term first, and then this big sum from L is equal to 1 to n. And now here's the beautiful thing. This term in brackets is the Pascal identity. N choose L minus 1 plus n choose L is n plus 1 choose L. That's the Pascal Triangle identity. So I can plug that in here, n plus 1 choose L, and then I have x to the L, y to the n plus 1 minus L. And then the last term is this blue term, n choose n, x to the n plus 1. And it's worked perfectly. I can rewrite this as the summation now running from L, running from 0 to n plus 1. N plus 1 choose L, x to the L, y to the n plus 1 minus L. And that's what I needed to prove. So that's a proof of the binomial theorem by induction. Okay, there's a very important special case of this where you only have one variable. So you set y is equal to 1, and you get 1 plus x to the n is summation from 0 to n, n choose k, x to the k. That's the one variable version of the binomial theorem. And we're going to derive a bunch of other properties of the binomial coefficients from this. So the first one is just take x is equal to 1, and you get the formula 2 to the n, n summation n choose k is equal to 2 to the n. That's what you get when you plug in x is equal to 1. And we saw this earlier. This has a combinatorial interpretation. This is the combinatorial proof of this is that both sides are counting the number of total number of subsets of an n set. But one of the nice things about combinatorics is there are many different ways of proving the same thing. Take x is equal to minus 1 on the other hand, and what you get is summation minus 1 to the k, and choose k is equal to 0. So the alternating sum of the binomial coefficients is equal to 0. And you can rewrite that as the following. If you sum up the binomial coefficients with k even and you sum it up with k odd, those two numbers are the same, and they're both equal to 1/2 of 2 to the n, which is to say 2 to the n minus 1. So the summation of the even binomial coefficients and the odd binomial coefficients are both the same. So let me write that out again here. I'll write it this way. And I'm going to indicate where these sums end. This dot is either n or n minus 1, depending whether n is even or odd, because that's the biggest even one. And then the biggest odd number less than or equal to n is n or n minus 1, depending whether n is even or odd. So that's the result. And here's a combinatorial proof of this fact. Whenever you see something like this, you think, well, maybe I can understand this from a counting point of view. The left-hand side counts the number of subsets of n with an even number of elements, even subsets. So how do you count those? Well, let's list the set as the elements 1 through n. And you know the way you make a subset is you go along for each element and you choose yes or no. Do you want it in your subset? That's where the 2 to the n comes from. And you go all the way up to n minus 1, and now the last one you can't choose, because if you're going to make an even set, the last one is determined. You either include it or not, depending on what you did previously. And this choice, there are 2 to the n minus 1 of those. And similarly, if you wanted to make an odd set, well, you just take the opposite choice. So both of these numbers are the same. You're just making the different choice at the last step. And both of these numbers are equal to 2 to the n minus 1. Okay, let's look at Pascal's triangle. I mentioned this earlier. Here it is. It's the triangle which displays this identity, Pascal identity, and it gives you this triangle like this, where each row is the binomial coefficients for a fixed n. And all of the identities involving the binomial coefficients, you can sort of look at them here. So for example, if you add up across a row, you get a power of 2. And on the other hand, if you take the alternating guys along the row, you get half that number, which is 8. And if you take the other ones, you also get 8. They don't match up pairwise, interestingly, but they still add up to 8. And if you take the alternating sum, of course, you get 0. And there are many, many other wonderful properties of Pascal's triangle. I'm not going to go into any of the other ones now. I just wanted to mention those couple of properties right here. All right, let's look at some more identities. There are many, many thousands of identities involving the binomial coefficients. I'm hitting the highlights. So let's look at the summation k runs from 0 to n choose k, x to the k is equal to 1 plus x to the n, the binomial theorem, in one variable. And let's take the derivative. That's an interesting thing to do when you have a polynomial. On the left-hand side, you get summation from 0 to n of n choose k, k, x to the k minus 1. And on the right-hand side, you get n, 1 plus x to the n minus 1. Now, whenever you do something like this, you have to be a little bit careful about the endpoints. If k is equal to 0, you're getting x to the minus 1 here. And that might look like trouble, except that the coefficient is in front of it is 0. So you're getting 0 times x to the minus 1, which is 0, and it's fine. This is exactly correct. And now set x is equal to 1, and you conclude that the summation of k times n choose k is equal to what? N times 2 to the n minus 1. That's interesting. It's the sort of weighted sum of the binomial coefficients where you weight n choose k by k. And you get something closely related to a power of 2, but it has this n in the front. Okay, well, that was interesting. Let's do it again. If we're taking one derivative was good, certainly taking two should be good. So let's see what happens. So here's what happens when you take the first derivative of both sides of the binomial theorem. You get this. So let's take d by dx of both sides again. So this time you get what? You get k minus 1, n choose k, x to the k minus 2. Oops, that's a misprint. N times n minus 1, x plus 1 to the n minus 2. Let's see. What does this tell us? Set x is equal to 1, and what you get is summation k minus 1, n choose k, is equal to n minus 1 times 2 to the n minus 2. Now, I'd kind of prefer if this was a formula for k squared times n choose k. It's not. It's k times k minus 1. But you can make it work. So if you split this up into two terms, you get k squared minus k times these sums is this thing. And that says that summation k squared and choose k is equal to, well, this thing I know. That's the previous result. So I can bring that to the other side. So remember that this thing is equal to n times 2 to the n minus 1. So I get a formula for k squared n choose k, which is n minus 1, 2 to the n minus 2, plus n times 2 to the n minus 1. And this right-hand side simplifies a bit. I can factor out an n 2 to the n minus 2 from both sides. And what do I get? N minus 1 plus 2. Indeed. And what does that give me? That gives me n times n plus 1 times 2 to the n minus 2. So here's a formula for summation k squared n choose k. I'll put it in red boxes here and over here. So the first time I did it, I got a formula for summation k and choose k, and here's the formula for k squared. And you can keep going like this. Of course, they get a little bit more complicated each step, but in principle, you could keep going. Okay, here's one more interesting identity. Summation n choose k squared, it turns out, is equal to 2n choose n. This is kind of a nice one. And the best proof of this is a combinatorial one. So the right-hand side counts the number of n subsets of a 2n set. So we want to see that the left-hand side counts the same thing. So let's write my 2n set as the set of numbers 1 through n, and then another n set, call it 1 prime through n prime. Okay? That's my 2n set, and I'm supposed to choose, I'm supposed to count all of the ways of getting a subset of this. Well, suppose S is a subset of this. I can write it as S union A, a disjoint union S intersect B, where A is the first n guys and B is the second. So to get a subset, you have to pick a subset of the first n and a subset of the second n. Okay, and S is supposed to be an n set. So if S intersect A is a k set, then S intersect B has to be an n minus k set. So how many ways are there of choosing S such that the first part has k elements and then the second part has n minus k? Well, the k elements from the first guy, there's n choose k of those. And then you have to choose n minus k from the second set. So this product is the number of ways of choosing S intersect A and times the number of ways of choosing S intersect B such that S intersect A has order k. Okay, and well, this number is n choose k squared because, of course, n choose n minus k is equal to n choose k. So there's my n choose k squared term. That's encouraging. So let's see what we have. What's the total number of ways of choosing an n subset of a 2n set? Well, it could have 0 elements from the first set, or an n from B, or it could have 1 element from the first set, and so on up to k elements and all the way up to n elements. So this guy here is the one I just computed, k from A and n minus k from B. So when you add those up, that's all of the possible n subsets of a 2n set, and that's your 2n choose n. Okay, that's all for that. Let's move on. The next thing I'd like to talk about is the generalized binomial coefficients R choose k. So what is n choose k? It's n factorial over k factorial n minus k factorial, where n and k, of course, are both integers. And you can write it like this: n times n minus 1 down to n minus k plus 1 over k factorial. That's a basic property. And when you write it this way, this particular formula, this makes sense. N doesn't have to be an integer. N factorial, n has to be an integer, but this thing, n times n minus 1 and so on, that makes perfectly good sense for n, any real number. And this is the kind of thing that you do often in combinatorics. You have a formula, and there are different ways of writing it, and one way has a particular property. This way has the property that it makes sense for n, any real number. Now what about k? So remember, n choose k is defined for k non-negative integer, an integer greater than or equal to 0. And keep in mind that 0 factorial is defined to be 1, and n choose 0 is therefore n factorial over 0 factorial n factorial, which is 1. Now, what happens when we generalize? Well, I'm just going to keep that. So here's the definition. If R is a real number, you define R choose k by this formula. It's R falling with k terms. That's sometimes the way you say this. It's R times R minus 1 down to R minus k plus 1, where there are k terms there, divided by k factorial. And this is defined for any real number R. And for this to make sense, you have to take k bigger than or equal to 1. But if k is equal to 0, you just define this number to be 1. And if k is less than 0, you define it to be 0. So the numbers R choose k are now defined for all real numbers R and all integers k. And this isn't just a formal game. There's these generalized binomial coefficients are actually quite useful, as we'll see in a moment. As we'll see in the next video.